Yeah. Okay. So I will introduce the next speaker also, and so it's really a pleasure to introduce Chakra Chennubhotla, and he comes from the Pittsburgh, I guess, consortium of pathologists, right? So he belongs to the Pittsburgh enterprise. And right now, he was an academic like many of us, not or maybe some of us, on this Zoom call. But right now is the CEO of Spintelex. So I'm not saying it right. Right. I'm sure I'm not saying it right. Chakra, please correct me at some point. So
No,
it's
you said it right. Thank you.
okay. Thank you. I think because I heard Mike say this word.
Spintelex, yeah.
Intellect, yeah, utter this word, like day before yesterday, right? Yeah, so it's a company dedicated to developing computational and systems pathology solutions, right? And it uses a lot of advanced spatial statistics and explainable AI technologies. So Dr. Chennubhotla, received his doctoral degree from, University of Toronto, from the Department of Computer Science, and he specialized in computer vision, machine learning, and AI. He was also an associate professor in associate professor in the Department of Computational Systems Biology at the University of Pittsburgh. So he's been building these systems for many, many years, right? And I guess he's made a transition to startups and industry, probably recently, right, Chakra, if I'm not mistaken?
Yes, very recently.
Yeah. So, and this particular system has shown up throughout throughout the workshop. I actually talked about it in my own talk, and Mike has mentioned it, and others have also kind of alluded to this to the system that Spintelex is working on. So I'm going to yield the floor to Chakra. You have about half an hour, Chakra. So
No
please,
problem.
maybe around 25 minutes or so. So, if you
Happy
can
to.
perhaps wrap it up, that would be great. Yeah.
Absolutely. So I want to make sure that you can actually see my screen.
Yes, we can. Thank you.
And I'm going to do just a simple slideshow. Yeah, play from start.
Looks good. Thank you.
Okay, so Dr. Machiraju, thank you very much. I would not have started in computational pathology, but for Dr. Bisich, when I met back in the university when I started, he was the one who motivated me to actually look at these data sets. And as you know, he has a big history on actually thinking about the whole slide image scanners and building them and all that. So really thanks to Mike and the team that I got in. And you also notice that I changed the title a little bit because the original title was Explainable AI for Anatomic Pathology. We published this in the Advances of Anatomic Pathology back in July last year. But I thought that part of this explanation is to tell you how and why is it that we are able to make these explanations. And hence I introduced the words spatial analytics with explainable AI for anatomic pathology. I started wearing this hat, the CEO hat of Spintelex, having taken a leave of absence recently. And part of this story is to tell you why we are so excited about this and how all this happened. I was very lucky with Mike and the whole lot of community of pathologists around us to educate people like me. And so greatly appreciate this opportunity to actually talk to people who are both, I'm sure there are pathologists here and also non-pathologists. Okay, so as to how I made the transition, and where I want to begin is to say that every tissue that you look at, whether it is diseased or whether it's healthy, has a story to tell. And so me as a computer scientist might just look at it as an image, but if you go talk to a pathologist, they have a lot to tell you just by looking at this tissue, and maybe with a bit of zoom, they know that this tissue is coming from a breast tissue, and they can tell you more than that. So with the interest that how do you actually build this narrative? What can this tissue reveal to you? And we feel that there were actually two elements in how you can go about doing this. One, I think you need to have a very intimate knowledge of the spatial architecture. What is it and where is it? And what are the changes in this from healthy all the way to disease? What are the changes that the tissue undergoes? And much of the changes with this tissue are to do with spatial. It's a spatial nature of this tissue that has been changing, that changes that you recognize and that the experts recognize, and then do diagnosis, do prognose, and do many other things based on the understanding of the spatial relationships. So here is a case wherein there are two parts to this story. One is able to understand the spatial, get a spatial understanding. I'm just going to use the broad term spatial analytics for that. And the second part of the story is that you're building this system, and you would like to actually go narrate the story to both the experts and also to the non-experts. First of all, to the experts, because you want to have them actually build trust in the system that you build. And there comes the story of explainable AI. So it's not just machine learning, it's just not AI. There's just another layer of understanding that you need to put in so that you can actually build the trust, make the system transparent, have the system actually learn from the feedback that the pathologists are likely to give you, pathologists, clinicians, oncologists. And there are many ways to probe this data set. So just to give everybody a bit of a background, and then I threw in, I emphasize both the words advanced and unbiased spatial analytics. That is because, hopefully you can see the cursor here. So there's a piece of tumor tissue on the left, and there are many ways you can take the entire section of this tissue and then do a whole slide image scanning, or you can take pieces of this tissue, which is typically what is done for genomics and other cases as well. But the idea and the picture on the right is a cartoon sort of representation of how this tissue might actually look like. And what I'm trying to sort of imagine here in this cartoon picture are three things. One, as a computational person, you think of, it's easy to formulate these cells as information processing machineries. And then, the first thing you ask is that what is the internal state of this machine, internal state of the state of the cell? The second thing is that how is this cell actually interacting with its neighbors? And that interaction, of course, is a spatial interaction with the neighbors. But that interaction doesn't stop just with the neighbors. It's also this entire environment. So here, I'm showing you two different environments. One, I'm calling it as microdomain 1. The other one is microdomain 2. And what's so special about these microdomains? And then the various shapes and colors are to tell you there are various cell types. Just recognizing what the cell type is a challenge in itself. And so, for example, if I have T cells, I'm showing them in different colors to highlight the idea that the T cells, it's not on and off. There are just a range of functionality, and then and the active is just not binary. There is a dynamic nature to this activation, and something that you want to capture from these data sets. So here, so in this cartoon picture, there are lots of these little drawings that I have to represent various cells. But what's so special and what's so different about these microdomain 1 and 2 is that in microdomain 1, just right off the bat, just by looking at colors, you can see that, oh, there's one tumor clone. I'm just going to call it tumor clone 1 that seems to be dominant. And then I'm also looking at lots of other kinds of cells here. And then I go look it up here and realize that, oh, there is a lot of immune cell infiltration and activation. And the analysis that I have done from this microdomain comes back and says, this microdomain has a low metastatic potential. And that's something that's very important to know up front by looking at the spatial configurations. What can you prognose about this? What might happen for this patient with this microdomain in place? But if you come to microdomain 2, very different. You have some rare tumor clones, 2 and 3. That means they don't occur frequently, but it's just not the frequency of the various cell types, but it's also the spatial interaction between the cells. So in this case here, I've deliberately drawn a microdomain wherein the immune infiltration is low. And I have a reason to believe, given the analysis that I'm going to do downstream, that it has a very high metastatic potential. Okay, so two things here that I want to communicate again is that it is just not about the frequency of these cell types, but it's also about the interaction between these cell types that play a huge role. And that is the spatial understanding of the tissue that you want to get. And not only that, it's not like somebody is actually drawing you where these microdomains are. Ideally, your system should be able to go and recognize where these microdomains are. So, and the reason to bring in, again, spatial analytics and explainable AI is to say that we are not just trying to do computational pathology, it's really computational systems pathology. If only the data is amenable for both the system's understanding of this tissue. And I'll take you through some of those ideas here that we have built and put together. So, and why does explainable AI matters? And given all the explanation that I have done, is that that without an understanding of this, so it's not just about, as I said, frequency, but it's also about the spatial understanding. You have given a better chance of understanding that there is a rare microdomain, rare because its occurrence is not frequent, and that potentially has a high metastatic potential, and perhaps it requires some targeted therapy. But if you take the more traditional route, it's possible that you're only looking at the most frequently occurring microdomains, which actually have low metastatic potential, and you might actually come back with an incorrect answer. Now, I'm actually going to show you an example of this for the colon cancer that we worked on in the next few slides. But the idea is that providing explanations for the recommendations that the system makes, it makes it transparent to the end users, builds confidence and trust. And I know there's been a lot of discussion already about these ideas. And without explanations, and I think there's less of a chance to convince the practitioners to actually use these machines. And we're at a stage wherein these computational and pathology systems should be really thought of as cognitive assistants. So there's both a perceptual component and there's a planning component, and then they can both together sort of help the practitioner, in this case, a clinician or a pathologist, to take the help of these systems. Okay, so just a brief take, because I come from Toronto, it's sort of obligatory to say what some of the people down there were saying about deep learning. But the idea is that this is Dr. Jeff Fine, who's at McGee Women's Research Hospital. So the question is that if you have a system that's providing decisions, how does Jeff actually reason with it? Why do you do that? Why not something else? When do you succeed? When do you fail? How can I trust you? When can I trust you? How do you correct an error? Those would be the sort of normal questions that an expert like Jeff would ask. Somebody who has been practicing this for almost 15, 20 years of diagnosing tissues and looking at least 60 to, let's say, 50, 60 or 100 cases per day. So you can imagine his experience is so much more involved in how to think about this. So with the idea that if you have the explainability and you make the system actually learn from the pathologist and provide feedback, and there's a better chance of Jeff acknowledging and say, okay, I understand why, but I think you're incorrect. Or I understand why not, but I think you're incorrect. So Jeff, as a pathologist, will have a chance to actually reason with the system and then provide further feedback as to whether those explanations work or do not work. So the challenge for us for quite some time now is how do you build these sort of explainable systems? And all the market research and all the people that we have spoken to have always come back and told us that the explainable AI will be the sort of game changer in adopting digital pathology. And the way I present this is just not about digital pathology, but this is really about computational and systems pathology. And I know there's already a discussion on the regulatory aspects, and I think all the regulatory bodies will continue to ask and will continue to pose questions about ML and the systems that you're using. And it's less about whether it is explainable, trustworthy, but more about saying, is it providing an adequate reason for the expert to believe and take action given that recommendation? Okay, so and then I stepped out, and then we started this company Spintellex with the idea that we want to harness the computation power of spatial analytics and explainable AI, and we should be able to turn this data that we're coming from both the preclinical and patient primary disease pathology. And I'll tell you a little bit more about why I use the word primary there, but really turn the data into knowledge that can inform therapeutic strategies and clinical decisions. And then the systems pathology is really forcing all the way down, all the way to drug discovery, all the way to therapeutic strategies, all the way to finding novel targets. So a very broad scope for what you can do by just looking at this tissue. And then if you look around and if you ask what are the unmet clinical needs, you see that there are many, both in how you analyze this tissue. Many times these technologies are limited to basic quantitation. They only tell you about the presence or absence of a biomarker or presence or absence of a cell type. And then almost always they're accompanied by black box AI. and they have very limited ability to identify the spatial tissue heterogeneity, just as I was pointing out before. For example, microdomain 1 and microdomain 2 being very different, not just in their composition, but also in the spatial interaction between the cells. And if you do that, that means you're setting up a system that's suboptimal in creating, accuracies for prognostic diagnostics, or has limited ability to selecting cohorts for clinical trials, and pretty much no ability to identify novel targets, drug discovery, or to recommend personalized therapeutic strategies. So here's our solutions, the HistoMapper and TumorMapper. And we took a broad view. We know the imaging can be all the way from transmitted light to multiplexed and hyperplexed immunofluorescence or mass spec. Multiplexed meant something like 9 biomarkers or less. But in the last year or a year or two, let's say, there are at least about a dozen platforms out there which can give you anywhere between 20 biomarkers to 75 biomarkers. And the idea of spatial analytics doesn't change. The idea of using explainable AI doesn't change. And you can also have a third way wherein you're actually combining both the transmitted light and the multiplex or immunofluorescence or imagery. So you also have this legacy data sets, and lots of labs have that, wherein you can run these sort of software on top of the data sets that have already collected and get additional information. So HistoMapper for traditional transmitted light imagery, TumorMapper for this multi to hyperplex fluorescence or mass spec based labeling and imaging. Okay. And what HistoMapper and the way we constructed the HistoMapper is that it should offer the complete spatial analytics, explainable AI, and the predictive computational guides on top of the standard analytics. So not just thinking in terms of the morphology, in terms of the cells, but also going to larger and larger structures and having a complete understanding of the tissue. So the pyramid that I've drawn on the right is just to show how the large amount of data that comes into the bottom part of this pyramid that starts slowly turning into knowledge with this additional spatial analytics and the explainable AI part. And just the pipeline in the way we thought about this is that in addition to doing all the basic processing that you need to do, such as stain color, how you normalize because you have data sets from different scanners and all. But some of the more important things that come in is that how do you do region of interest segmentation, wherein you minimize the annotation burden on the experts. You do this entire process in an unsupervised way, and you're very good with using the spatial analytics, the spatial analysis or the spatial statistics of the tissue in recognizing these regions of interest. And many times you have both the transmitted light in two forms, both the HND and IHC that you want to combine so that you can do some systems pathology for having used some additional biomarkers in addition to the morphology and all that you're getting from the transmitted light, right? So with that, with the HistoMapper, we have a whole range of applications that we're targeting, not just in prognostic diagnostics and clinical trial stratification, but also in the intelligent case triaging and retrospective quality assurance. In the intelligent case triaging is wherein when you get a new pathology case, you are trying to decide whether it should be sent to an expert to review this, or it should be sent to any anatomical pathologist, because there could be just a case of cancer versus no cancer. But many times it could also be possible that there is this borderline case and you need this expert to actually take a look at it. And that's something that we also got back from talking to the pathologists, from talking to the clinicians, that these borderline cases, and even more so in the systems that we've been working with, particularly in HistoMapr-Breast case, that the borderline cases such as the atypical ductal hyperplasia and all take up a lot of their time in diagnosing. So if you want to really push AI or the explainable AI or the machine learning or the spatial analytics, here's a case wherein these borderline cases provide you an ideal test scenario to push your technologies to do well. So, and one of the first things that we had to do is how do we actually interact with the pathologist? And here's a case wherein with a, it's a whole slide image viewer. You have all the tissue slides on the right side, and you can zoom, pan, do all the stuff, and then some clinical information as well on the left side. Also some provisional diagnosis, and I'll come to that in just a second. But what the software actually does is loads up and then automatically detects these regions of interest. So these are drawn in green. This is actually the boundary detected by this unsupervised and automated region of interest extractor, right? And then it further does something else. It lines up all the regions of interest in a way that the regions of interest in the front, in the beginning, are the ones that are of critical importance. And as you go down the scroll bar here, then you have regions of interest that are less and less diagnostically important. So, and the idea is really the following, that you want to meet this, you want to definitely help with the software like HistoMapper, the efficiency and accuracy of the pathology workflows, and also in the patient cohort stratification for clinical trials. And the idea is that instead of doing a very sequential scanning of the tissue, why not show regions of interest with the, with the increasing diagnostic importance or decreasing diagnostic importance, so that there's no delay in the discovery, and then you are minimizing the errors that can that are being made, and still cover 100% of the tissue, so that the pathologist still feels very comfortable for having looked at the entire tissue. And I just want to support that in terms of both the efficiency and accuracy, we worked hard in showing how much time is saved by the pathologist by looking under the microscope versus looking through the HistoMapper in making diagnosis. And you can see that consistently we've been getting very good efficiency results. And in the hard case, as I said, the borderline case of detecting the high risk benign breast lesions, not cancer, no cancer, but this is benign lesions, so that you want to know what to do with the patient, what kind of regimen that you want to put the patient through. It turns out that we have one of the best state-of-the-art results in diagnosing, differentially diagnosing the high risk benign lesions, right? So with that, so that sort of motivates us to why we lined up all the regions of interest at the bottom with the decreasing diagnostic importance. And then the software, HistoMapr-Breast, also puts out this label, this recommendation that the image, the region of interest that it is seeing, is actually atypical ductal hypoplasia. Okay, and then the pathologist in their hands can click on the Y button. It comes up with an interface which actually explains to the pathologist what the key findings are and what the recommendation is and how confident the software is. And they can further go and take a look at which regions and what are the spatial nature of this tissue type that enabled the recommendation of atypical ductal hypoplasia. So here are the cases wherein I'm pointing out to various regions in this particular region of the tissue, and then also saying what is the relative importance in actually assigning these, in using these local regions in coming up with this diagnosis, right? So increase the enhanceable, increase the explanatory power, increase the interpretability, make it transparent to the pathologist, and that's a sort of goal. And the pathologist, if they can agree, if so, they can click on that. If they disagree, that's also fine, and then it goes as a feedback to the software, to HistoMapr-Breast, or they can just say, oh, they're not very sure. And either way, they can finalize and go to the next case. So that's the idea with which we build the HistoMapr-Breast. We are collaborating with Cellnetics. It's a very large private pathology practice with an extremely large number of breast biopsies per year. And we are validating HistoMapper in the clinical setting. Okay. So very quickly, I want to take you through, I spoke a lot about HistoMapper. I want to take you through TumorMapper a little bit to further demonstrate the idea of how the spatial analytics and explainable AI come together. And in this case, explainable AI is a lot easier because the systems pathology and the systems biology is staring at you. So now it is the question of how quickly can you get to the systems biology to explain to the clinician, in this case, let's say an oncology, a medical oncologist or a surgical oncologist, how quickly you can explain what pathways might be playing a role, and what is the network of these pathways that's probably driving the recurrence. So, and the way we did it is that we could work with any image data sets. We are not the instrument company. We are only working on the software. It could be from any imaging platform, any reagent type, and any disease. Although I've been talking a lot about cancer, but we could work with other diseases as well, and we have done that as well. And the way, again, same sort of a pyramidal nature to how the information goes through the system. At that base level is where I call that the TumorMapper basic, which basically does all the basic image processing and the quantitation. And the HistoMapr-Breast does all the spatial analytics, taking you all the way to the systems biology and being able to provide the explainable AI guides while sitting on top of the HistoMapr-Basic. Okay, so there are, as I said, there are at least 10 or 11 platforms out there which are already generating multi to hyperplex labeling data, and then we take that, do the basic image processing, quantitation, and measurement with HistoMapr-Basic, feed that into HistoMapr-Advanced, which does the spatial analytics and explainable AI, and then run it through. And this now becomes the backbone for the explainable AI guides. And in this case, I'm going to show you at least of the many applications that I have listed here, I'm going to show you something about the prognostic. So one of our first product would be the HistoMapr column. And this is the work that just appeared in Nature Communications a few months ago. And so here we are using CellDye, which is one of the multiple hyperplexing imaging platforms that were available to us when we started this work with in collaboration with GE Global Research. And we are using several biomarkers to sample the tumor microenvironment and building some user interfaces, and I'll get to that in just a second. But we were careful in terms of how we think about the functionality and the activation status of the cells. So we do some automated cell phenotyping. And with that, we are able to say which cells are specialized, which cells are transitional. So are they undergoing EMT transition and so on. And then there are some that are multi-transitional cell states. And then ask a very critical question here in terms of microdomains. How do I discover these microdomains? Is to ask, is there an automated way of finding a distinct configuration of these phenotypes that can emerge with some metastatic potential, with some recurrence potential? In this case, the outcome is the predicting the risk of recurrence. So I can actually attach a number to each one of these microdomains and say, this microdomain is probably driving recurrence within 3 years, but this microdomain here is not really causing the recurrence to happen within 3 years. So we have been able to do that. This work all appeared again, as I said, and going back to the point as to why you want to think in terms of spatial analytics, here's the case where I'm showing this risk of predicting recurrence. And if you were to use the clinical variable alone or the intensity of the biomarkers, this is the sort of AUC values that you get, which is about 0.72. But once you bring in this spatial analytics, you see that my AUC values really jump up a lot higher. So vastly superior performance with the use of spatial analytics. I don't need to stop there. I can now go back and ask, what is the network biology? Which biomarkers are talking to whom? And how are they different between patients that have no recurrence or no recurrence within 8 years versus patients with recurrence within 3 years? And that then leads me to ask what pathways are collaborating or cooperating or not cooperating. And that leads us to discover new drug targets and so on. So just in the interest of time, I listed out all the sort of work that appeared that drove some of this analysis here. And I also want to just as a wrap up to say that it's just not computational pathology, but it's all computational systems pathology. It's here. And but we need trust and transparency to be built in, accountability as well, and for early clinical applications, I think this is the key. And the explainable AI is just augmenting the pathologist, not replacing, obviously. The pathologists and the clinicians will remain in control of the process and the final decisions. And what the xAI can do is just to provide the assistance. So with that, it's a whole team that worked for many years now, including an NSF SBIR grant that we got to actually test and validate HistoMapr-Breast. With that, thank you very much. And I know I'm just out of time. Thank you.
Thank you, Chakra, for a really enlightening talk. So we are certainly out of time. It is an extremely, expedient question, we can perhaps entertain. Anybody? In that case, why don't we actually move on to Mike's talk? And if anybody has more questions for Chakra, please, use the chat box. So, I think I also have a lot of questions, but I'll probably, reach out to you separately, Chakra. Thank